righty, lads and ladies, welcome back to pre-calculus. Just 1 second to get some papers here, and we can get started. I know some of you are a little bit nervous about exam 2, and if you look on the syllabus, we're supposed to be having exam 2 very soon. We're going to be a little bit off from the syllabus dates, and that's okay. This is normal. Remember, the syllabus dates are just approximate, just to give you a rough feel for when things are going to be happening. Today, I'm going to talk a little bit about the exam, when we're going to have it, what's going to be on it, just to make sure we're all on the same page, because I don't want anybody panicking. And then we're going to move forwards and do the last section on polynomials, which is talking about complex numbers, complex roots of polynomials, the fundamental theorem of algebra. It's really good stuff. I think you're going to like it. Yes, the beard is gone. Florida summers are difficult to get through with a beard, so I lose patience with it towards the end of the summer. And then also I have a 5-month-old son who's getting stronger and stronger, so he pulls on it. You know, it was cute at first, but he's just too damn strong for that now. He's getting kind of thin. He pulled so much of it out, we figured just get rid of it. All right. Here we go. Let's do the thing. It's a little bit sad. I used to tell my Calc 2 students when they learn about power series, which is a pretty intimidating topic for that class, that I'm not really good at power series. The beard just whispers to me about them in my sleep, and now I can't make that joke anymore. It's a little unfortunate, but we'll get through it. This is MAC1140, section number 008, which is pre-calc, and today is the 12th of October, 2021. So what's on the docket? Today we're going to talk a bit about exam 2. And then we're going to talk about complex numbers. Complex roots. And the fundamental theorem of algebra. So that's the plan. First things first, let's talk a little bit about the test. Right, so exam 2 is quite naturally going to cover all the stuff that we've talked about since exam 1. So that's polynomials, right? Polynomials are what we've talked about so far. And then the material that remains to be discussed for exam 2 has to do with rational functions, which are like fractions made up of polynomials, and inequalities, inequalities involving polynomials and involving rational functions, which is a little bit of a throwback to section 1.8 that we talked about at the very start of the term, but we're going to approach it from a slightly more advanced perspective. And now that we have all these factoring skills, there will be a bunch of problems that we couldn't have solved before that we can now solve. All right, so that's what's on the test, right? All the polynomial stuff starting at quadratics, moving up through rational and polynomial inequalities. So basically all of chapter 3. When is the test, right? So we have, including today, we have, I think, 3 more sections before the test. So there's today's section, which is on complex numbers and the fundamental theorem of algebra. We have the section we're going to talk about on Thursday, which is on rational functions and their graphs. And then we have a section we're going to talk about next Tuesday, which is on rational and polynomial inequalities. So 3 more sections before the test, which means next Tuesday, I'll be finishing the material that's going to be on your second test. So probably the test will be late next week, next Thursday. So here we go. Let's write this stuff down. Exam 2 will cover quadratics, all the polynomial stuff, rational functions, and polynomial and rational inequalities. So 3 more sections. The date for exam 2 is most likely And let's see, we said next Thursday. I think that's the 21st, right? Yeah, 21st. Now, if, for example, the rational function section ends up taking more than one day to cover, or if the section on rational and polynomial inequalities just feels really shaky, anything like that, I'll be looking at your homeworks and your quizzes, stuff like that to help decide. Oh, that reminds me, we need a quiz. So also, I guess today is our last day talking about polynomials. So there will be new homework today. And a new quiz. So we'll probably do 2 quizzes before the next test. One quiz I'll put out there today, and then the other quiz I'll probably put out there Thursday or early next week, probably early next week, because I want to be able to include the polynomial and rational inequality section on it. So again, test 2 either next Thursday or the following Tuesday, depending on how quickly we move through that stuff. If we need a little more time, I'm okay with doing it the Tuesday after, but no later than that. Let me put that here. You can write that in your notes. No later than Tuesday. What's the date on that following Tuesday? 26. So definitely no later than the 26th for exam 2. Split, rotate. Here we go. Let's get that clock up there. Okay. New homework today and new quiz. Yeah, new homework and new quiz coming up today. Okay, I think that's all that stuff. Are there any questions about kind of the roadmap, where we're going, what you need to be working on or worried about, anything like that? Okay, then let's talk about complex numbers. So what is a complex numbers? Or what is a complex numbers? What is a complex number? Anybody help me out with that? Is it just a number that is more complicated than regular numbers? It means something specific? Just trying to gauge your exposure here. No bad answers.
It's just not a natural number?
Not quite. So a natural number, remember, is a non-negative whole number. So like natural numbers include 0, 1, 2, 3, 4, 5, and so on. The real numbers are an example of a set that is larger than the natural numbers. Integers are also an example of a set that's larger than natural numbers, response to the chat. Rational numbers are also a set that's larger, or in some sense more complicated than the natural numbers. But the complex numbers, oh, I left off the L, complex numbers. These are numbers that involve the square root of -1, right? These are numbers that can be written in the form. So a complex number is a number of the form a plus b times I, where a and b are real numbers and I think most of you have some familiarity with the number I. Most often it's introduced as the square root of -1, but it turns out there's a small problem with that definition. Every number has 2 square roots. So the better way to define I is by saying I squared is -1. You could also say I is the positive square root of -1, but when it comes to complex numbers, talking about positive and negative turns out to be a little bit complicated because they're not an ordered field. So you may recall that at the very beginning of the semester, I said the real numbers are the unique, meaning the only complete ordered field. Complex numbers do form a field, meaning we can add, subtract, multiply, and divide complex numbers. And they are complete. Also, they're in that same sense that there's no gaps in the real line. There's no gaps in the complex plane, but they're not ordered. They can't be placed onto a line. It turns out they're two-dimensional. And I'll be a little bit more clear about that in just a second. So a complex number is any number of the form a plus b times I, where I is this number such that when you square it, you get -1. And most people learn it as I is the square root of -1. We use the symbol I here because it stands for the word imaginary, and it's actually a pejorative. That word imaginary was a term that mathematicians coined because when these numbers were first discussed, most mathematicians just didn't like them. They were like, there is no number such that when you square it, you get -1. If you multiply a negative times a negative, you get a positive number. Multiply a positive times a positive, you get a positive number. So how could you possibly have a number that when you square it, multiply it by itself, you get -1? And the answer is, well, there is no real number that does that. But we can invent or define I to be the square root of -1. We can define the number I to be the number such that when I multiply it by itself, I get -1. This question in the chat, are irrational numbers complex numbers as well? Yes, but maybe not in the sense that you're thinking. So this leads me nicely into a very sneaky fact. So if you see this, any number of the form a plus b times I is technically a complex number. And a sneaky fact, which can be used to create good true-false questions. Oh, and I should say, sorry, let me add something here before I talk about the sneaky fact. The complex numbers, the set of all complex numbers, is denoted with a Blackboard bold C. So you remember we use the Blackboard bold R to denote the set of all real numbers, right? The R with like 2 legs. This is the symbol if you want to talk about all the complex numbers, like throwing all of them into one basket. And now the sneaky fact, and this answers a few of the questions from chat, is that the real numbers are a subset of the complex numbers. In other words, every real number which means every, not just every real, right, not just like, every real number is a complex number. And since the natural numbers, the integers, the rationals are all real numbers, all of those things are complex numbers. The number 2 is a complex number. Every real number is also complex, is a complex number with imaginary part. The number b is called the imaginary part. Equal to 0. Right, so in this form, a plus b times I, a is called the real part and b is called the imaginary part. Well, if you want to write, you can write any real number in this form. So example, 2 can be written as 2 plus 0i. So yeah, natural numbers are complex numbers. -5 can be written as -5 plus 0i. So every integer is a complex number. 3/8 can be written as 3/8 plus 0i. And the same thing, any rational number could be written as a complex number. And indeed, the irrational numbers also, like pi. Pi is a complex number. It's pi plus 0 times I. So this just serves as, it's a sort of fun fact and you want to think about, and it makes for kind of good silly test questions that just ask whether you kind of understand the structure of these things. Every real number is a complex number. The real numbers live inside the complex numbers. They're just all the complex numbers whose imaginary part, the b here, happens to be 0, right? If b is 0, the I goes away and you just have a. So you can write any real number in that form, which means every real number is a complex number. And that includes, question in chat, it includes the irrational numbers, right? Irrational numbers like pi can be written in the form a plus bi. The complex numbers live in a plane, live in a two-dimensional plane called the complex plane. And again, we usually write C for that in the same way that we write R for the real line. So they can't be put into a line. There is no way that you can impose what's called a total order on the real, on the complex numbers. No, the stuff we're learning today most definitely is on exam 2. Yeah, this stuff and the 2 next sections are on exam 2. Exam 2 is going to go up through rational and polynomial inequalities. All right, so here's a two-dimensional plane. Instead of calling it x and y, I'm going to call this the real line, or RE, and I'm going to call this the imaginary line, IM. And the way you graph a complex number, right, like a real number, you can graph it by putting it on the line. Yeah, and we saw that when we like graph intervals and stuff. The complex numbers, in order to graph a complex number, because it has kind of 2 parts, a and bi, you need a two-dimensional space to do that. So for example, if I want to graph the complex number 3 plus I come out, the real part there is 3, so I would come out 1, 2, 3, and the imaginary part is 1. So this would be the number 3 plus I graphed in the complex plane. The number I itself is right here. The number 2I is right here, right? And this is the normal real number 1, real number 2, real number 3. Down here we have negative I and negative 2I. And over here would be like negative 1, negative 2, negative 3. The complex number, negative 2 minus I, or negative, let's do negative 2. Yeah, negative 2 minus I, right, whatever, right here. This would be negative 2 minus I. Just like this is 3 plus I. Right, so complex numbers live in a plane. I'm going to show you some very pretty pictures a little later today. Remind me if I forget to do it towards the end of class, where graphing complex numbers you'd be surprised how beautiful this can be. But that's it. So they're two-dimensional objects. They live in a plane. The plane is called the complex plane. And to graph a particular complex number, you go out along the real line to the real part, and then you go up the imaginary part. So like 3 plus I, you go over 3 and then up 1. Turns out that the arithmetic of the complex numbers has a really nice geometry. They're so beautiful that many mathematicians, even if they don't want to answer questions about complex numbers, work with complex numbers to answer their questions. So for example, my own research was in additive number theory, which means I work with questions regarding addition of whole numbers. And that might sound boring to you, but I promise there's some interesting questions in there. But the way you get work done in that field is by studying these things called basic hypergeometric series, where you're looking at functions whose inputs are complex numbers. It turns out that because the geometry of the complex plane is so beautiful, oftentimes the best way to answer a question about the real numbers or about natural numbers is by complexifying it, looking at the equivalent version of that question in the complex numbers, and then coming back to work in your original domain after solving the question in C. There's a famous quote here. I think it was, I forget, Polya maybe, or Halmos, one of those famous Hungarian mathematicians, who said, the shortest distance between 2 true statements on the real line, right, here's the real line, the shortest distance between 2 true statements on the real line loops through the complex plane. which is, you know, him just being cute and saying, you know, working with complex numbers makes life easier. Turns out multiplying complex numbers is equivalent to like rotating in this plane. Adding complex numbers is equivalent to vector addition in this plane. If you've ever heard of vectors before, it's really beautiful. So there's a lot of nice geometry here, which we're not going to get into, but I just want to tell you exists. The complex numbers form a field. Meaning we can add, subtract, multiply, and divide any two complex numbers. You can also raise them to powers, and we're going to talk about that too, but they form a field the same way that real numbers do. And I want to show you how to add, subtract, multiply, and divide complex numbers. You're not going to need to do a lot of division of complex numbers in this class, but in future classes, it will show up. So I'd be doing you a disservice if I didn't show you how to do arithmetic with these things. So I want to do an example where we just do some arithmetic. Once you see it done, it will not be complicated, I promise. Perform the indicated operation. So let's look at some addition. How about 3 minus 2i plus, and I'll write these in parentheses, plus negative 6 plus 4i. And part B, let's do some subtraction. How about 1 plus I minus, it doesn't matter, 5 minus 2i. Let's do some multiplication. How about 7 minus 3i times 4 plus 2i. And then lastly, we'll do some division. Actually, let me add one more here. And 3 plus I times 3 minus I. There's some special cases of multiplication I want to look at. We'll also look at some division. So how about 1 minus 3i divided by, I don't know, how about 2 minus 5. Right, so just basic arithmetic with complex numbers. Turns out it's not too bad. Essentially, you treat I as a variable, right? You treat I the same way you would treat X. The only difference is anytime you run into I squared, you replace that with -1, right? Because I is the number such that when you square it, you get -1, the square root of -1. So you treat I like a variable, meaning we're going to have to do some foiling when we go to distribute, like when we go to multiply. And when you do operations like addition and subtraction, you just combine like terms. All right, let's do it. So for parts A and B, I'll just put the solutions up here. As I said, you combine like terms. So if numbers do have an I, those are like terms. And if numbers don't have an I, those are like terms. So this would be 3 plus -6, or 3 minus 6, and then minus 2i plus 4i. So you put the real parts together and the imaginary parts together. 3 minus 6 is -3. And -2i plus 4i, again, you treat I like a variable. So like -2x plus 4x would be +2x. So this is +2i. So we have -3 plus 2i. Our goal is always to write the answer in the form a plus bi. And that's what we've done here. A, the real part is -3. B, the imaginary part is 2. When we perform subtraction of two complex numbers, the only thing to be careful about is make sure you distribute this negative. That's why I'm writing these in parentheses. If I didn't write the parentheses around 5 minus 2i, you might get the feeling that you're just subtracting the 5, but you're subtracting the whole thing, 5 minus 2i. So here, I would write this as, I'll first just distribute 1 plus I minus 5 plus 2i. And now it's just like the previous problem, just combine like terms. So 1 minus 5 is negative 4. And I plus 2i is 3i. And that's the job done there. And for parts C and D, I'll do the work below because we're going to need a little more space. So if I want to multiply 7 minus 3i with 4 plus 2i, the game here is to distribute. Again, just treating I like a variable. So my first 7 times 4 is 28. My outers, 7 times positive 2i is plus 14i. My inners, minus 3i times 4 is minus 12i. And my lasts, negative 3i times positive 2i would be negative 6 times I squared. Now this is definitely not in that form a plus bi. I can combine these two, that's easy, but I need to do something with this I squared. So my next step here, I'll just write 28, and then positive 14 minus 12 is positive 2, so that's plus 2i. The tricky bit here is to remember I squared is negative 1, right? So this is minus 6 times negative 1. And then following your order of operations, negative 6 times negative 1 is positive 6, so that's 28 plus 6, which is 34 plus 2i. Since this is the first time we've seen this, any questions about what we did here or where things came from? So the only thing we had to remember there is that I squared is negative 1. We'll look at powers of I, higher powers of I in a second. All right, if we're all feeling good about that, I'm going to do the next one, which is 3 plus I times 3 minus I. And you're going to see something neat happens here. If I FOIL, same as before, my firsts are 9, right? 3 times 3. Then I have minus 3i from my outers and plus 3i from my inners. And then positive I times negative I is minus I squared. And again, I squared is negative 1. The cool thing here is that plus 3i and minus 3i, those add up to 0. So this is 9 minus negative 1. Right? Minus, and then I squared is negative 1, so this is 10. The thing that's going on here, you notice this is a real number, right? If I wanted to write this in standard form of a complex number, it would be 10 plus 0i. Right? Because there are no i's left here. So you could just write 10 if you wanted, if that makes you feel strange, but this is the same as 10 plus 0i. And the fact that this came out to a real number has to do with the relationship between these two. These are what are called complex conjugates. You remember early in the semester when we looked at simplifying some of those difference quotients, when those difference quotients involved square roots, one of the algebra tricks we used to clean them up was multiplying by the conjugate. That term conjugate comes from complex numbers, comes from this concept of a complex conjugate. So what is a complex conjugate? a plus bi has complex conjugate a minus bi. And it turns out that if you multiply a complex number by its complex conjugate, you always get a real number. And that real number is the square of what's called the modulus. So you graph these two complex numbers, 3 plus I and 3 minus I for you. So up here is I, down here is minus I, and this is 1, 2, 3. So in the complex plane, 3 plus I is right here. And 3 minus I is right here. The number that you just saw us come up with, 3 plus I times 3 minus I, is the square root of this distance, called the norm or modulus of 3 plus I. It's the same as the square root of this distance, right? Those two distances are the same. So this would be the square root of 10. And you can get that thinking about right triangles. Yeah, if you look at the little right triangle here, 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 then a squared plus b squared equals c squared. And it's just a nice fact that a plus bi times a minus bi is the square of the norm or modulus of that complex number. This is not something you need to know for our class. It's just a cute fact that I wanted to share with you. But what is a complex conjugate? You do need to know that, right? If I ask you what is the complex conjugate of 7 plus 10i, you need to be able to tell me it's 7 minus 10i. So if you change the plus to a minus, or the minus to a plus, right? If you swap I with its negative, if you change the sign of the imaginary part, that's called the complex conjugate of the original. Okay, let's look at division. Division is the one thing that's a little bit complicated here. So we want to divide 1 minus 3i by 2 plus 5i. It turns out the trick for these, right? It's not at all obvious how you would write this in the form a plus bi, because the top is like a plus bi, the bottom is like a plus bi. You could try dividing kind of like we divide polynomials by treating I like a variable, but that is more complicated than it needs to be. The trick to dividing complex numbers, if the denominator is non-real complex, then what you do is you multiply top and bottom by the complex conjugate of the denominator. So I multiply by 2 minus 5i over 2 minus 5i. Because that will make the denominator real, right? Like we just saw, if you multiply a complex number by its conjugate, you get a real number. So the downstairs here after I do this will be a real number, which makes life much easier. Remember, fractions always have their tops and bottoms in parentheses, so we need to FOIL. Upstairs there, I'll have 2 minus 5i, and then minus 6i, and then negative 3i times negative 5i is positive 15 times I squared. And we do the same thing downstairs. We FOIL it out. So 2 times 2 is 4. And then minus 10i for my outers, plus 10i for my inners. And then 5i times negative 5i is negative 25i squared. And we can clean this up. Numerator here is 2 minus 11i plus 15 times I squared is minus 15. Because again, I squared is negative 1.
I have a question, Shannon. Shouldn't 15 be negative?
No, because this, well, not in this line. Negative 3i times negative 5i, the two negatives make the positive. And then I times I is the I squared. So negative 3 times negative 5 is positive 15. And then I times I is I squared. When we simplify the I squared, it will become negative, but the I goes away.
Yeah, okay.
Bueno? All right, and then downstairs, the minus 10i and positive 10i, those go away. They add up to 0. So I just have 4. And then minus 25i squared is plus 25. Again, because I squared is negative 1. So if we put all the pieces together, 2 minus 15 is negative 13, and I still have my minus 11i. And downstairs, 4 plus 25 is 29. And now that the denominator is real, we can split up the fraction. This is negative 13 over 29 minus 11 over 29 times I. And this would be the standard form of that complex number. Any questions on this guy? Okay, then the last bit of kind of complex arithmetic I want to look at with you has to do with powers of I. You remember the other day when I talked about Évariste Galois and how he, among other things, proved that there could never be a formula for the roots of a fifth degree polynomial? The way he did that was by essentially inventing a new field of mathematics, group theory, right? So he didn't invent group theory, but he invented this whole new field of group theory. Group theory was originally discovered by looking at powers of I. So group theory is the study of a certain kind of algebraic structure that originated by looking at arithmetic operations which cycle. And it turns out that powers of I cycle. That might be a little surprising. So I'd like to look at that with you, some powers of I. So we're going to look at I to the 0, I to the 1, I to the 2, and I to the 3. That's how we're going to get started. I to the 0, because anything raised to the 0 power is 1, I to the 0 is also 1. Oh, there's a question. So do we need to separate into two fractions? Well, remember, we always want to write this in the form a plus bi. So here, a would be negative 13 29ths, and b would be negative 11 29ths. So we do want to split it up. That is preferred. If we're trying to write our answers for complex numbers in standard form, then we would prefer to have this answer. Certainly, I wouldn't want like this answer. This is pretty opaque. I don't really know much about this from that thing. If you left it like this, I wouldn't mark it as wrong necessarily, but you need to know how to do this. Maybe a half point, something like that. So yeah, we do want to get here. We want to see the real part and the imaginary part. All right, let's come back down here. I to the 0 is 1 because anything to the 0 is 1. I to the 1, well, anything to the first power is just itself. So that's I. I squared, by definition, is negative 1. So what is I cubed?
Would it be I?
Almost. So
Negative 1?
getting there, let's put those last two answers together.
Negative I.
Negative I.
Negative I, yeah. So I cubed is I squared times I to the 1, which is negative 1 times I. So that's negative I. Can we use that same logic to figure out I to the 4? Well, whatever it is, just like we said with I cubed is I squared times I to the 4 is I squared times I squared, right? That's how exponents work. Like x squared times x squared is x to the 4. And then each of those, I squared and I squared, are negative 1s. This is negative 1 times negative 1, which is positive 1, the same as I to the 0. So I to the 4 is I squared times I squared. Each of those I squareds is negative 1, so that's negative 1 times negative 1. And if you multiply negative 1 by itself, you get positive 1. I to the 5, well, that's I to the 4 times I to the 1. And I to the 4 we just saw is 1. So this is 1 times I. And 1 times anything is that thing. So I to the 5 is the same as I to the 1. It's just I. I to the 6. There's a few ways we could justify this. We could look at it as I cubed times I cubed, or I'll do it like this. It's I to the 5 times I. Since I to the 5 is the same as I itself, this is I times I, or I squared, which is negative 1. And you see now why I'm arranging it in this way. I to the 0 and I to the 4 are the same. I to the 1 and I to the 5 are the same. I squared and I to the 6 are the same. So can we guess what I to the 7 might be?
Negative I.
Yeah, negative I, right? This is, and we can justify it if we want. This is I to the 6 times I, which is negative 1 times I, which is negative I. And we guessed it. We didn't even need to do that just based on the pattern. It turns out, that this is intimately related to that thing called the Euclidean algorithm. So if you're trying to compute a power of I, what you need to know is where are you in this cycle? It will always be one of these numbers, either 1, I, negative 1, or negative I. And the question is, where are you in that cycle? Which is the same as asking, what is the remainder when you divide that power by 4? Right? Like I to the 7. Well, what's the remainder when you divide 7 by 4? 4 goes into 7 once with a remainder of 3. Okay, the remainder is 3. That means it's the same as negative I. A fun question to ask about these sort of things. It's 2021 now, right? What is I to the 2021? Any takers on this? Yeah, Christopher's correct. I to the 8 and I to the 12 would also be 1.
Negative I.
Yeah. Actually, no, sorry, not negative I. So I to the 2021. This is the same as asking, remember, what is the remainder? When we divide 2021 by 4. So the powers of I cycle every 4. So if you want to know where you are in this loop, you just have to know what's the remainder. Yeah, very good. It would be I, because 2020 is divisible by 4, right? So here's how I would write this. I to the 2021 is I to the 2020 times I to the 1. And since 2020 is divisible by 4, leaves a remainder of 0 when you divide by 4, I to the 2020 is 1. And the crucial step here is that this piece is equal to this piece because 2020 is divisible by 4. So in other words, if you write the power in that form QD plus R, just as integers now, then the QD part will go away and you just have the R. So these are fun and also kind of make for good, tricky little exam questions. Later in your mathematical careers, when you learn about power series, if you're lucky, if you have a good Calc 2 teacher, you will prove a very important theorem by a man named Euler, Leonhard Euler. Some people mispronounce it Euler, but it's not, it's Euler. You'll learn a theorem due to Euler relating the function e to the x to the two trig functions sine x and cos x. And the proof of that theorem revolves entirely around this business that powers of I cycle, which is very, very cool. All right. I think that's enough kind of talking just about complex numbers. So I'd like to get back into polynomial land. What does any of this have to do with polynomials? Well, there's something called the fundamental theorem of algebra. And that word fundamental is a pretty important word. The word theorem is a pretty important word, right? Fundamentals, like in basketball, the fundamentals are dribbling and shooting layups and stuff, the basics. Fundamental is like foundational. And theorem is an important statement which is true. So this is the foundational statement which is true about algebra, kind of the most important thing. It might not sound super surprising given what we've already learned, but it took thousands of years to prove this. And no proofs, by the way, that I'm aware of can avoid complex analysis. They require some pretty heavy-handed methods. So we're not going to prove this theorem. I'm just going to show it to you. This says, any polynomial of degree n, that's something like p of x equals an x to the n plus an minus 1 x to the n minus 1 all the way down to a1x plus a0. Any polynomial like this, any polynomial of degree n, has exactly n roots when counted with multiplicity. So you noticed in your homework, right, where you had roots of multiplicity 2, you had to list them twice. Where you had a root of multiplicity 3, you had to list it 3 times when they asked you for the roots of the zeros. That's to connect to this idea that a cubic polynomial always has 3 roots. A quartic polynomial always has 4 roots, but only when you count with multiplicity. Moreover, if and these are complex roots, right? These roots can be real or complex numbers. If we write C1, C2, all the way out to Cn for those possibly complex roots, then P of x can be expressed in factored form as, and this you kind of already know, or just saying it is true in general for complex numbers as well, some constant times x minus c1 times x minus c2, right? Each one of those roots tells us a factor. And what this theorem is saying that this is true even for complex roots. And most importantly is the first part, that a polynomial of degree n has exactly n roots. Okay. Your book states these as several theorems. They combine two, they kind of split this theorem up into two. They call it the fundamental theorem of algebra and the complete factorization theorem. That's not how most people would say it. This is how most people would say it. So an example here real quick. Let's look at the polynomial p of x equals x cubed minus 1. Normally, we think of this as having only one root, right? Let me show you the graph. We can graph this as a transformation, right? It's x cubed shifted down 1. So if I take my normal x cubed graph, which is this S curve going through the origin, and I shift it down 1, that looks like this. It has the one real root here at 1, which you can find by setting x cubed minus 1 equal to 0 and solving by taking cube roots. But it also has two complex roots, two non-real complex roots. So the question becomes, how do you find those non-real complex roots? So let's express this. So let's express p of x in fully factored form. Well, I would use my rational roots theorem. Generate my list of p's and q's. P's would be divisors of the constant term, plus minus 1. Q's would be divisors of the lead coefficient, also plus minus 1. So our possible rational roots are just plus minus 1. And we know from the graph that 1 is the rational root, right? This does not have an x-intercept over here, just over here. So if I divide x cubed by x minus 1, remember p of x, here's 1x cubed plus 0x squared plus 0x minus 1. So if I want to do that division, I would put the 1 here and then 1, 0, 0, negative 1. I bring this down. 1 times 1 is 1. 1 plus 0 is 1. 1 times 1 is 1. 1 plus 0 is 1. 1 times 1 is 1. Negative 1 plus 1 is 0. So I learned that I can write this polynomial as x minus 1 times x squared plus x plus 1. Now that x squared plus x plus 1 is what's called an irreducible quadratic. What I've done here is I've factored x cubed minus 1 into a linear real factor and an irreducible quadratic factor. And it turns out you can always do this. There's a theorem I'm going to show you in a minute that says every polynomial with real coefficients can be factored into linear factors with real numbers only and irreducible quadratic factors. What the fundamental theorem of algebra says is that we should be able to get it into this form if we're willing to work with complex numbers. So in other words, I should be able to factor this thing further. And how would we factor this quadratic further, given that we can't factor it by hand? What did we do last time when we ran into stuff like that?
Quadratic formula.
Yes, ma'am. We're going to use the quadratic formula. So now we use on x squared plus x plus 1. His roots would have to be, I'll write the formula. It's negative b plus and minus the square root of b squared minus 4ac all over 2a, which is negative b is negative 1 plus and minus the square root of 1 squared minus 4 times 1 times 1, which is negative 3, all over 2 times 1 is 2. So here's our first opportunity to practice working with complex numbers as they arise. What is the square root of negative 3? Well, whatever it is, it's the square root of negative 1 times positive 3, right? Negative 3 is negative 1 times positive 3. And we can split up that square root. This is negative 1 plus or minus the square root of negative 1 times the square root of 3. Square roots play nice with multiplication. They don't play nice with addition or subtraction. They do play nice with multiplication. So when I've got a product under my root, I can give the root to each separately. And then this piece, the square root of negative 1, that's I. So this is negative 1 plus or minus I times the square root of 3 all over 2. In other words, these roots are negative 1/2 plus square root of 3 over 2 times I, and negative 1/2 minus the square root of 3 over 2 times I. And if you're taking trigonometry right now, you may recognize 1/2 and root 3 over 2 as values from your unit circle. I'm going to graph all of these in the complex plane for you in a minute. You'll see what's going on. Something quite beautiful is happening. But before we do that, let's finish factoring this. So p of x, I just need a little more space here, is x minus 1. And then I have x minus negative 1/2 plus root 3 over 2 times I, and x minus negative 1/2 minus root 3 over 2 times I. This would be my fully factored form. And if I graph all of those complex numbers, here's where things get quite beautiful. This is the complex plane C. The first root is a real number, is 1. I'll put 1 right here. That means negative 1 would be like right here. So negative 1/2 would be like right here. The square root of 3 over 2 is a little bigger than 1/2, but smaller than 1. So here's root 3 over 2I. And here's negative root 3 over 2 times I, which means those other two roots are right here and right here. This is negative 1/2 plus root 3 over 2 times I. And this down here is negative 1/2 minus root 3 over 2 times I. And they live on the unit circle in the complex plane. So this is something that may be especially interesting to my people who are currently taking trigonometry as well as pre-calculus. If you look at the unit circle in the complex plane, these three roots of my polynomial x cubed minus 1 form an equilateral triangle in the complex plane on the unit circle. in the complex plane. This is really quite beautiful. And if you wanted to express these using trigonometric functions, you absolutely can. They're quite beautiful. This is like the point -1/2 √3/2, which you know from trigonometry is 2 pi over 3. And this one would be 5 pi over 3. I'm sorry, 4 pi over 3. That's not pertinent for our class, but it is a very beautiful fact. These are called roots of unity. So let me put this is. These are called the third roots of unity, i.e. the 3 cube roots of the number 1. So normally we think of there as only being 1 cube root of 1. It's the number 1. But if you're willing to think about complex numbers, there's 3 cube roots of 1, 4 fourth roots of 1, 5 fifth roots of 1, and so on. And they always form a regular polygon in the complex plane on the unit circle, which is just amazing. This blew my mind the first time I saw it. For us, you just need to know, for our purposes, right? For the purpose of our test, you need to know how to arrive at this, nothing more. Yeah, so no, you're not going to have to graph anything like this on the test. All you'll need to do for the test is arrive at this. But I want to show you some pictures later that will help you understand this a little better. And it's just quite beautiful. I'd be doing a bad job as a math professor if I didn't show you, because it's so amazing. Okay. Let's get a little bit more practice. I want to show you one more theorem, and then we're going to work more on factoring over the complex numbers. There are some tricks and things that are relevant. So let me go ahead and share this with you. The first relevant theorem, not trick, I'll give you both of them here. There's kind of 2 theorems we need to talk about. First, if P of X is a polynomial with real coefficients, let me say it this way, if A plus BI is a non-real complex root of a polynomial with real coefficients, then so is its complex conjugate. A minus BI. So if I tell you that 1 plus I is a root of a polynomial, you automatically know that 1 minus I is also a root of that polynomial. Complex roots come in conjugate pairs. That's how I remember this theorem. Complex roots come in conjugate pairs. It comes from the quadratic formula. It's actually a consequence of the quadratic formula and this other theorem, which says any polynomial with real coefficients can be factored into, so according to the fundamental theorem of algebra, we already know that if you have all the roots, real and complex, that you can write the fully factored form of that polynomial. But if you just want to stick to real numbers, you can factor any polynomial into real linear factors and real irreducible quadratic factors. And if you look at the example we were just playing with, p of x equals x cubed minus 1, we were able to factor that a couple different ways, right? We were able to factor that as x minus 1 times x squared plus x plus 1. This is the linear factor. And this is the irreducible quadratic. Right? So we haven't involved any complex numbers at this stage in the factoring, right? Everything here is real numbers. So if you're wanting to work only with real numbers, not non-real complex numbers, then the deepest thing you can say about how factorable any polynomial is that you can write it as a product of real linear factors and irreducible quadratic factors. A test for irreducibility to check if a quadratic is irreducible. Anybody know how to do this? We've talked about it once before. Remember, irreducible means doesn't have any real roots, cannot be factored over the real numbers. What test do we have to see if a quadratic has any real roots?
The rational root theorem?
Rational roots theorem gives us a list of possible rational roots, but it doesn't tell us about real versus complex roots. So think way back. Think back to when we talked about quadratic functions. We compute the discriminant. B squared minus 4ac, right? The result from before was if b squared minus 4ac is negative, then the quadratic is irreducible. The quadratic doesn't have any real roots. So we just have this new language now. We can, if b squared minus 4ac is less than 0, then ax squared plus bx plus c has no real roots, which means it's irreducible. So this is just a quick way to check if your quadratic has any real roots or not, right? This is the part that's under the square root in your quadratic formula. So if this is negative, then you're going to get some i's, which means that this quadratic can't be factored over the real numbers. In other words, it's an irreducible quadratic. So this theorem is not especially useful for us, but it is a big deal in the sense that it says a lot about polynomials. For example, there are no irreducible cubic polynomials. Any polynomial of degree 3 must have a real linear factor, because it can either be written as all linear factors or linear factors times irreducible quadratics. Since the degree is odd, one of the factors has to be linear. Okay, and then we saw that if we continue to factor this polynomial, I'm going to need the space here, it's x minus 1 times x minus negative 1/2 plus the square root of 3 over 2 times I times x minus negative 1/2 minus the square root of 3 over 2 times I. Those roots are complex conjugates. right? Because the only difference in them is the sign of the imaginary part. One has a plus √3/2i, the other one has a minus √3/2i. So this example here is just to illustrate the two theorems, right? You can factor any polynomial into linear and irreducible quadratics. And if you're willing to work with complex numbers, you can further factor, and the roots that come from those irreducible quadratics will be complex conjugates. And that comes from the plus or minus in the quadratic formula, right? You've got negative b plus or minus the square root of b squared minus 4ac, blah, blah, blah. That plus and minus is what gives you the plus here and the minus here, which guarantees that any of the complex roots that come from an irreducible quadratic will be complex conjugates of each other. Pretty cool stuff. Okay. There's a handful of things that we should practice at this point, one of which is finding all the roots of a polynomial. We have talked about that. We've done one thing here. We took a cubic and found all the roots, real and complex. Another thing we should practice is finding a polynomial that satisfies certain conditions, right? So I give you the roots and you find me the polynomial. That's something we've done before, but we've never done it with complex numbers. So I want to practice that. And it'll also give us opportunity to employ this first theorem, which is absolutely something we will need to use in this class, right? So the second theorem here, not so much something that you'll use, it's something that will show up like on the way to factoring, but this first theorem is something that you absolutely need to solve problems. So let's look at an example of a problem that we solved by employing that theorem. Find a polynomial of degree 4 with roots I, 2, -2, and having P of 3 equals 25. So the first thing you need to do is come up with your factors. And to come up with your factors, you need to know all the roots. So remember, roots and factors tell us about each other. So my roots, I'll list the real ones first, are 2, -2, and I. Is there anything missing from my list of roots? Think about that first theorem.
Missing an additional root.
Yeah, which one is missing? What's missing? What must be a root that isn't yet?
Is it the conjugate?
The complex conjugate of?
I.
Very good. What is the complex conjugate of I?
Negative I?
Very good. I is 0 plus I, so its complex conjugate is 0 minus I. This one comes from the theorem. And if we forget to add him to this list, we wouldn't be able to get the right answer. It's very important that we remember complex roots always come in conjugate pairs. And I'll tell you right now, there will be a problem on the test, very much like this, right? Very much like this, where you need to remember to include a root that is maybe not explicitly listed. All right, the other hint here is that the polynomial is supposed to be of degree 4, right? But I've only given you 3 roots. And remember, when we look at all the roots of a polynomial, real and complex, the number of roots, when listed with multiplicity, should be the same as the number of factors, right? Should be the same as the degree. So if the degree is 4, I need 4 roots. All right, so the factor I learned from the root 2 is x minus 2. The factor I get from the root -2 is x plus 2. The factor I get from the root I is x minus I. And the factor I get from -I is x plus I. Now, according to the fundamental theorem of algebra, P of x is some constant, the lead coefficient, times all these factors, which is x minus 2, x plus 2, x minus I times x plus I. Again, don't forget this lead coefficient, right? We're going to need to solve for him. And if you forget him, then you won't be able to make this true. So please, on any problem like this, where you're saying find a polynomial satisfying some conditions, remember to leave room for this lead coefficient. You have to solve for this at the end. Now, how am I going to solve for this lead coefficient? Well, I got to multiply all this shit out. Multiply all this shit out, and then I can plug in 3 and set that equal to 25. That will allow me to solve for A. Thankfully here, the multiplication is not too bad. I'm going to do it in groups of 2. I'll do the x plus 2 times x minus 2 and the x plus I times x minus I. Then I'll distribute those because these are nice. So x plus 2 or x minus 2 times x plus 2 is x squared plus 2x minus 2x minus 4. Should have left a little more space there. X minus I times x plus I is x squared plus ix minus ix minus I squared. Sorry about the spacing. Let me zoom in a little bit. So the middle terms vanish in each of these. This is a times x squared minus 4 times x squared. The middle terms vanish here also. Minus I squared is minus -1, is plus 1. Now, if we continue foiling, right, normally it's possible that each of these would be a trinomial with 3 terms, but here we got lucky because there's some nice symmetry. If we continue multiplying these out, x squared times x squared is x to the 4 minus 4x squared from my inners plus x squared from my outers makes minus 3x squared. And then minus 4 from my lasts. Now I want P of 3 to be 25. We could go ahead and say this is ax to the 4 minus 3ax squared minus 4a. Either one of these forms will work for what follows. Sometimes these are said, you know, instead of saying P of 3 is 25, they say the coefficient of x squared is 7 or something like that, you know, and then you would take this information and solve for a. But let's go ahead and plug in 3. We know that when we plug 3 in to this function, the whole thing should be equal to 25. Let me move to another page. I'll write the 25 on the left. 25 equals, what is P of 3? Well, it's a times 3 to the 4 minus 3a times 3 squared minus 4a. And I can solve this for a. I think the fastest way to do that would be to factor the a back out. 3 to the 4 is 81. 3 squared is 9 times -3 is minus 27. And then you've got your minus 4 here. So we've got a times 81 minus 27 minus 4. Let's see, that's 81 minus 31, which is 50. So 25 equals A times 50. Means A has to be 1/2. And thus P of X equals, I'll write it in the other form here. This is 1/2. Well, I'll write it in the last form. Why not? 1/2 X to the 4 minus 3/2 X squared. And then minus 4 times 1/2 is minus 2. So this would be our final answer here. So it's just a way of these problems getting a teensy bit trickier, right? Because you have to use your theorem to deduce this last factor. And you have to do some complex arithmetic when you multiply things out. You got to work with the eyes. It's not that bad though. Are there any questions about any of these steps? Alrighty then, that's where we're going to end it for today. This is kind of the full story on polynomials. How did I get this? So I took my A equals 1/2 and I plugged it back in here. So if we take A 1/2 and we plug it in for A here, then we get this. All right, 1/2 times x to the 4, 1/2 times 3ax squared, and 1/2 times -4. This is really as much as you guys are expected to know about polynomials coming into calculus, which is great news, right? We can factor them even with complex numbers. We can graph them as long as we know the end behavior and the local behavior near the roots. We're going to use this now as we move into rational functions, which are ratios of polynomials. We're going to be working on drawing really nice graphs of ratios of polynomials, and we're going to be working on solving inequalities, and understanding the graphs is going to be crucial to solving those inequalities. So I'm going to put up a fresh homework for you guys today that is just this complex number stuff. And then on Thursday, we're going to start talking about rational functions. Alrighty, if there's anything you guys need, you can come to me in office hours, Monday, Wednesday, Friday, 1 to 2. You can talk to me on the Discord or Canvas message me, whatever you like. Be mindful that exam 2 is just around the corner. We're getting close, probably next Thursday, maybe the Tuesday after. And you're going to have 2 quizzes between now and then to help you prepare. That is it. I'll see you guys next time.